Hello viewers, welcome to take you through the story of A-level physics paper 2. And this video we are going to go through the topic of magnetism and alternating current. In particular, we shall look at calculations involving specifications of the Earth's magnetic field. So this is what we hope to upload. These are like the subtopics under the main topic of magnetism and alternating current. So what is ticked means it's already available on the platform, and what is not yet ticked means will be uploaded with time. And like I've already told you, we are interested in the calculation bit of it, but complete notes are found in the books I recommend. There is, for physics, there are 4 books. There is Physics Paper 1, Physics Paper 2, Topical Question Bank, and its solutions. For principal mathematics, there are still 4 books: Math Paper 1, Math Paper 2, Timely Past Papers with marking guides, and Topical Question Bank. Subsidiary math is only 1 book. So for copies, I encourage you to call on this number or send a WhatsApp message to make an order. So Earth's magnetic field. So when you get a magnet and you suspend it at any one place on the Earth's surface, it sets with its north pole dipping below the horizontal in the northern hemisphere. Remember, the Earth is divided in two hemispheres. We have the northern hemisphere and the southern hemisphere. So if you are in any country in this northern hemisphere and you suspend a magnet, it will lie so that the north pole is below the horizontal. When you are in the southern hemisphere, it will lie in such a way that it is the south pole which is dipping. We are interested in this word dipping because some we are going to talk about angle of dip. So dipping below the horizontal in the southern hemisphere. So when that happens, it implies the angle which the magnet makes with the horizontal is what we call the angle of inclination, or in short, angle of dip. Remember, we are under specifications of the Earth's magnetic field, so we shall need those terms: angle of dip, angle of declination, meridians, magnetic and geographical, and all those. So this is what I'm trying to mean. If you get a magnet, so when you get a magnet and you suspend it, in this case it is the north pole which is below the horizontal. So the angle it makes between the horizontal line and the magnet is what we call the angle of dip. This term will be vital when it comes to calculations. Angle of dip. Then the vertical line through the vertical plane in which the magnet comes to rest in is what we call the magnetic meridian. Okay, so now, since the magnet always sets along the magnetic field lines, it implies that the angle of dip keeps changing from place to place on the Earth's surface. So this angle of dip is not constant throughout the whole world. So when you're in one country, maybe among the West African countries, the angle of dip is different than when you're in southern countries, like that, or along the equator. So the angle of dip keeps on changing from place to place. That's what you should always remember. Then the vertical plane in which the magnet sets is what we call the magnetic meridian. So the magnetic meridian is inclined to the geographic meridian through an angle which we call the angle of declination. So now we have 2 things. We have what we call angle of inclination and angle of declination. So let's look at these planes. For example, if that is the Earth, we have what we call the true north and the true south. These are the true north or geographical north, and this is the true south or the geographical south. Then this one, which is tilted away from the true north, is what we call the magnetic north, like this. And now this one is what we call the angle of declination. So the Earth has a magnet inside, is taken to be a big magnet with the north pole here and the south pole here. So that's why the field lines are running in that direction. So you put a magnet in the northern hemisphere, it will rest with the north pole below the horizontal. Southern hemisphere, it rests with the south pole, below the horizontal. Now a plane through the geographical north and geographical south is what we call the geographic meridian, just as you can see here. Then a vertical plane through the magnetic north and the magnetic south is what we call the magnetic meridian. So this is representing this, and this is representing this. So the angle between the two meridians is what we call the angle of declination, like that. So the vertical plane through which the Earth's geographical poles, the vertical plane which passes through the Earth's geographical poles, that is geographical north and geographical south, is what we call the geographic meridian. I think we have seen that. Then since the angle of dip changes from place to place, it implies that the magnetic meridian also changes. Remember, the magnetic meridian is the vertical plane through the magnetic poles. So that means that even the angle of declination keeps on changing. So it is only the geographic meridian which is constant. So we shall go to some of the specifications of the Earth's magnetic field. So the Earth's magnetic field is often called its total intensity, represented by capital H, can be specified by the vertical and horizontal components HV and HH respectively, as shown below. So you shall have the magnetic meridian and also so that meridian has a horizontal component of the total intensity and also a vertical component of the total intensity. Then the resultant will be in that direction. That is called the resultant intensity. The angle between the horizontal component and the resultant is what we call the angle of dip. Then the geographic meridian will be in that shape. And remember, the angle between the two meridians is what we call the angle of declination, theta. So from this one, we realize that it's a right angle triangle. This is the right angle triangle. So I can say cos theta is equal to adjacent over hypotenuse, which gives this, or sine sigma. So sine sigma will be equal to opposite over hypotenuse, which is this, and cos sigma will be equal to adjacent over hypotenuse, which is that. So that implies that also tan theta, I'm used to theta, so tan sigma, it will be equal to HV, which is the opposite over HH, which is the adjacent. Then by Pythagoras theory, resultant will be got by this expression. So we have two terms, what we call intensity and also magnetic flux density. These two are related by what we call permeability. So magnetic flux density, which we now know, is equal to permeability of free space multiplied by the total intensity. So that means that the Earth can also be represented in terms of magnetic flux density, as shown below. So the meridians remain the same. We are just changing the intensity and replacing it with the flux density. Just as you see here, this is now BH. Initially it was total horizontal component of intensity, but now it is horizontal component of flux density. This one was vertical component of intensity, now it is vertical component of flux density. And this one was the resultant intensity, now it is the resultant flux density. The angle remains the same. Then we have the geographic meridian, whereby the angle between the two meridians is what we call the angle of declination. So still BV will be equal to B sine angle of dip. Then BH will be equal to B cos angle of dip. And tan angle of dip is equal to BV over BH. So we should be used to these formulas because we shall use them more frequently in the calculations. So BV is the vertical component of the magnetic flux density and BH is the horizontal component of the magnetic flux density. So with that, we shall go through some questions. Question 1 came from U.A.C.E 1999, paper 2, question 5C, and it says, a circular coil of 20 tons each of radius 10 centimeters lies flat on a table. Okay, the Earth's magnetic field intensity at the location of the coil is 43.8 amps per meter, while the angle of dip is 67 degrees. Find Roman 1 the magnetic flux threading the coil. Then Roman 2 the torque on the coil if a current of 2 ampere is passed through it. So I'll make a sketch. Of the intensity. So B is equal to this. So we shall substitute. This one is a constant and this is the intensity, which is amps per meter, to give you the flux density. And area is pi r squared because it is the circular coil, to give you this. But remember, they asked for magnetic flux, and remember magnetic flux is what? Magnetic flux linkage is NAB and the B is BV. So substitute number of turns, cross area, and BV to give you that as the flux linkage. Then Roman 2, they wanted the torque on the coil if a current of 2 ampere is passed through it. So total flux will be mu naught total intensity, to give you this. Therefore torque will be Barney cos theta. So Barney flux density, which is this, area, number of turns, current, and the theta. So simplifying gives you this as the torque. So actually here it is Newton meter, not just Newton, Newton meter. Then question 2 came from U.A.C.E 2006 part 2, question 5C Roman 3, and says, find the force per unit length on a straight horizontal wire carrying a current of 2 amps in the direction north to south if the angle of dip is 70 degrees and the Earth's horizontal field component is this, that is BH now. So that is the current. Then we have the side is a horizontal wire, so that is BH and this is BV, and the resultant is in that direction. So completing the triangle gives you that. So we know BH is this, and we know the angle of dip is 70, which is that. So that means we shall be able to get the value of BV. After getting the value of BV, we can now get force per meter. Remember, F is equal to BIL. So when we divide both sides by L, this side we get force per meter, and this will be B times I. And the B is BV. So substitute and get the answer they wanted. Question 3 came from U.A.C.E 2004, paper 2, question 7D, and says, an aircraft flying horizontally at 800 kilometers per hour at a point where the Earth's magnetic flux density is this, and the angle of dip is 60 degrees. If the distance between the wing tips is 50 meters, calculate the potential difference induced between its wing tips. That is now induced EMF of a moving conductor. So it is moving with the velocity of this. This will be the horizontal component, then this will be the vertical component, then the resultant, and the angle of dip. So B, velocity converted to meters per second, which is that. Then BV can be got by resolving B to the vertical to give you B sine 60, which is this. Then induced PD is B times L times velocity. So BV is here, length and velocity, and that will be the induced PD. Then question 4 came from U.A.C.E 2010, paper 2, question 5F, and says, an aircraft of wingspan 20 meters is moving horizontally from west to east at a velocity of 250 meters per second in a place where the angle of dip is 40 degrees. The EMF induced across the tips of the wings is 6 millivolt. Find the magnetic flux density of the Earth's field. So we shall repeat the sketch same as before. Put the velocity, then the flux density, horizontal component, vertical component, resultant, and completing a triangle. So we shall repeat the same. Induced EMF is BV LV. So induced EMF is this. It was in millivolts, so you convert to SI unit. BV, L, and V. V is the only unknown, so you can get it. Then you can, but remember they want the resultant. So now that I have BV and I have this angle of dip, I can use the two to get the value of B. So substitute and get the value of B. And that's what they wanted. Now we shall go to what we call a deflection magnetometer. Deflection magnetometer is also known as a tangent galvanometer. So those two words mean the same. And they said it's a scientific instrument used to measure currents, to measure small electric currents, and it operates based on the principle of the tangent law of magnetism. So it consists of a vertical scale, of a vertical circular coil, and a horizontal circular table, pivoted with 3 leveling screws on which a compass box is supported. The compass box consists of a small pivoted magnet to which a thin long aluminum pointer is fixed at right angles. So let's begin with a circular base, and it has screws to leveling screws to keep it leveled horizontally. So the third screw is the other side, which is invisible. Then from there we shall need a compass box. Compass box is attached to a circular table, which is that, and the compass box has a small magnet and a pointer. Small magnet. This is a small magnet. This is the pointer. Then we also have, now this compass box is, this circular table is horizontal. Now the coil is vertical, what we call circular coil. It is vertical. The reason is to keep their fields perpendicular. Then these screws are the inlets of current. Inlets of current. So when you pass current through the coil, a magnetic field will be generated. So initially, before you feed in current, it is on, the field is only due to this magnet. So you shall have a horizontal component. When you feed in a current, then the coil also, because current will be passing through the coil, and a magnetic field will be generated due to the coil. So the pointer can rotate over the circular scale graduated in degrees. Okay. The compass box is supported such that the center of the pivoted magnet coincides with the center of the circular coil. So it is used to compare. So this deflection magnetometer is used to compare two magnetic flux densities, but one of them should be the horizontal component of the Earth's flux density. That is why you saw a small magnet attached to a pointer. A magnet attached to a pointer. So when no current flows through the coil, there is only BH, and the pointer is at its initial position. So when you look from up, this is what you'll be seeing. So you have two zeros because the pointer is two-way. The pointer is two-way, like that. So that's why you have 0, 0. So even here there will be 45, and also here 45, like that. Even here there will be 45, and also here 45, like that, because the pointer is two-way. And this is the BH due to this small magnet. Now, what happens when we feed in a current? So when current is passed through the coil, the flux density BC due to the current flowing through the coil is perpendicular to the horizontal component BH. And due to the interaction of these two fields, the pointer deflects through an angle theta, which such that it points in the direction of the resultant field of both BH and BC. So the angle is measured. So let's see what happens. We shall have that such scale. Now the magnet is going to tilt because of the interaction of the two fields. That is why it is now tilted. It was initially vertical, now it is tilted. So that means that the pointer will also point in that direction, because the angle between the magnet and the pointer should always be 90. So this is now the field due to the coil, and I think it's perpendicular to that of the horizontal component. So you can extract out this direction, which is here, and also this, which is here, and you can use it to get the resultant flux density, BR. And the angle between, I think you see this angle, theta, is between the BH and the new position. Like that. So according to tangent law, it implies that tan theta is equal to BC over BH from the triangle we drew, and BR is got by Pythagoras theorem. So assuming that the coil has n turns, radius r, and is carrying a current I, Then BC at the center is given by that. I think you saw this from in the video of Biot-Savart law. So remember, it's about comparison, meaning that if tan theta is greater than 1, it implies that BC is stronger than BH. So with that, we shall go through some questions. Question 1 came from UNEB 2016, paper 2, question 6C, and it says, a circular coil of 4 turns and diameter 11 centimeters has its plane vertical and parallel to the magnetic meridian of the Earth. Okay. Determine the resultant magnetic flux density at the center of the coil when a current of 0.35 ampere flows in it. So take the horizontal component of the Earth's flux density to be this. So flux density due to this circular coil is given by this. So substitute constant, number of turns, current, and radius. So that gives you the flux density as that. So if BR is the resultant flux density, then you shall use Pythagoras theory to come up with the resultant they want. Then tan theta is equal to this, implying that the angle is 45. Then question 2 came from UNEB 1994, paper 2, question 5E, and it says, a circular coil of 5 turns of mean diameter 10 centimeters is mounted with its plane vertical and along the magnetic meridian. A small compass needle is mounted on a vertical axis at the center of the coil. When a current of 0.5 ampere is passed through the coil, the compass needle deflects through 61 degrees. When the current in the coil is reversed, the compass needle deflects through 59 degrees. So calculate the horizontal component of the Earth's magnetic field intensity. So 1, the average deflection will be 60 degrees. Then the radius is this, half of the diameter. Then for the circular coil, BC is equal to this expression. Substitute to get the flux density for the coil. Then you know that tan theta is equal to BC over BH. But remember, they asked for HH, which is the intensity, and so that B is related to H in this expression. So when I make HH the subject, I'll come up with this expression. So substitute to get the intensity they wanted. Then question 3 came from UNEB 2011, paper 2, question 5C, and says, a coil of 50 turns and radius 4 centimeters is placed with its plane in the Earth's magnetic meridian. A compass needle is placed at the center of the coil. When a current of 0.1 amps passes through the coil, the needle deflects through 40 degrees. When the current is reversed, the needle deflects through 43 degrees in the opposite direction. Roman 1. Calculate the horizontal component of the Earth's flux density. So 1 is the average deflection, which is that. Then for the circular coil, flux density is given by this expression, so substitute to get the flux density. Then you know that tan is equal to BC over BH, meaning that BH is equal to this. Substitute to get the output. That was Roman 1, then Roman 2. Calculate the magnetic flux density of the Earth at that place, given that the angle of dip at that place is 15 degrees. So when angle of dip is 15 degrees, we can use cos. So it all comes from the other diagram we've been drawing, which is this. So this is B, this is BH, and this is the angle of dip. So the adjacent is BH and hypotenuse is B. That's why we have used cos. Then make B the subject, and that is what they wanted. Question 4 came from UNEB 2000 paper 2 question 5D, and it says a circular coil of 10 turns and diameter 12 centimeters carries a current I. The coil is placed with its plane in the magnetic meridian. A small magnetic needle placed at the center of the coil makes 30 oscillations per minute about a vertical axis. When the current is cut off, it makes 15 oscillations per minute. If the horizontal component of the Earth's magnetic flux density is this, calculate the magnitude of I. So the assumption is that assume that the square of the frequency of oscillation is proportional to the magnetic flux density. So radius is that, and frequency per second, because what we were given was per minute. Per second we come up with that. So the result can be BR. We know that frequency, square of frequency is proportional to flux density. That means that F1 over F2 everything squared is equal to BR over BH. Substitute for F1, F2, and for BH to come up with the value of BR. Now from Pythagoras theory, BC will now be given by this, which gives you that as the density of the coil. Then for the circular coil, BC is given by that. So we know B, we know the constant, we know the number of turns, we know the radius. What we need is the current. So make it the subject. You will come up with value I. So that brings us to the end of this video. Thank you for watching.